also speak about, okay. I will also speak about these coefficients IP, and they will surprisingly involve multiple zeta values. I will give you the definition of multiple zeta values and alternating multiple zeta values in a few minutes, because they appear in this description, and these values are really important in number theory. This is a very, very hot research topic with 600 plus papers. If you look up the references online, there's, I mean, in the last 20 or 30 years, this topic has exploded, and surprisingly, it also appears in relation to these families of integrals. So this is where analytic combinatorics and number theory meet in some sense. And there's also a third topic which comes into play here, namely probability theory, which is also very close to my heart. And I will interpret this very honest looking or simple looking integral in terms of sequences and convergence of moments. And this is nice that you have three different aspects, analytic combinatorics, number theory, and also probability theory, all meeting at such a simple problem, and you can put this into a very nice context here. So, and the interplay of all these three aspects lead to a very precise understanding of such integrals and also related problems. So I will embed this later into a more general context. Yeah, first I will speak about these integrals, these coefficients, I beg your pardon, which appear in the asymptotic expansion and their combinatorics. So for all of you which have a background mainly in probability theory, this will be an excursion to analytic combinatorics and number theory. But to put you onto safe ground later on, we will embed this problem into a more general context, and I will try to give you a greater perspective. Why is this simple problem worthwhile to study using a probabilistic interpretation of this problem setting? Okay. First of all, because the multiple zeta values appear, I will give you a short introduction to the multiple zeta values. Of course, I think all mathematicians know the ordinary Riemann zeta function, and the multiple zeta values actually stem back to Euler. Euler already considered multiple zeta values where we have nested summations for positive integers k greater or equal 1 and arguments I1 up to ik, where I1 is larger or equal to, I'm sorry, this 2 is also allowed. We can define a corresponding multiple zeta value, which is such a nested sum. And Euler already considered such multiple zeta values, and the number k here is called the depth of it, and the sum of the i's is called the weight. And why are these values important? I mean, the Riemann zeta function is already very important, and also the multiple zeta values are really, really of importance. Of very intriguing and remarkable identities, and there are many, many, many conjectures about them which are unsolved at the moment, and they also appear in applications, not only mathematics, and they appear in a great many different areas of physics, particle physics, Feynman diagrams, knot theory, quantum field theory, and many more. They also appear in the description of the quicksort algorithm in probability theory when you look at the cumulants of the Gumbel distribution. So they appear not only in physics but also mathematics, and also applications like the quicksort limit law. You can see that the moments, the cumulants involve multiple zeta values. So this often appears. Okay, so these are the multiple zeta values. They are basically nested sums, generalizing the Riemann zeta value, but they are also colored or alternating multiple zeta values where you allow where we put a bar here over the arguments, and here we have that they are alternating. So the alternating zeta values are called alternating because they alternate in sign, and every time we have a bar here, then this means we have a -1 to the power of n1 or n2 and so on. So these are also nested sums but alternating. And note that these multiple zeta values, they converge unless I1 is an unbarred 1, and they are also related to the logarithm functions, because, for example, zeta of bar 1 is minus the logarithm of 2, the natural logarithm, and there's this general relation which was already known to Euler, if I'm not wrong. Okay, now, a shorthand notation. If there are a lot of ones in the put these into curly brackets in order to ease the notation. This means I have L different ones. So it's this is a nested sum, and also for alternating zeta values, I will have this shorthand notation. So now we are ready to dive into our big problem, namely their coefficients IP of this integral and their relation to multiple zeta values and their alternating counterparts. So first of all, one can look at the dominant term. In general, these coefficients can be tackled using analytic combinatorics. This is what Guy Louchard did at the beginning. And we will have a look at the dominant coefficient. We can just evaluate this integral for small n, do some computer experiments, and these evaluations suggest that, of course, this converges and that we have 3/4 should be the value. And I will give you much more than here this I0. I will give you I1, I2, and so on, using a machinery stemming from analytic combinatorics. And how do we do that? Of course, we will prove that 3/4 is correct, and much more using the apparent symmetry of the integral at 1/2. So I can use the symmetry to split the integral in halves. And then I do another substitution in order to get a different representation of the integral. Of course, it still looks quite intriguing. So what do we do next? We dive into analytic combinatorics. We use we try to do asymptotics, and this gets more messy. So we use another substitution. This is basically what this was Guy's idea, and we use the exponential logarithm presentation to get a much more involved representation of this integral. You see that I have now here power 1/2n, and here now the boundaries of the integral involve this n. Now we can do an asymptotic analysis, but the price we pay is that the integrand here gets more and more complicated, and when things get more messy, what is the thing to do? Just introduce a shorthand notation and somewhat hide the difficulty. So once we have this shorthand notation capital A for the integrand, we have here a compact representation of what we want to analyze, and we are interested in an asymptotic series when n tends to infinity. So what do? We expand this exponential function e to the power a into powers of this shorthand notation a, and if we split this integral, we already can show that this 3/4 is correct, and we can also show that the second term I1 equals 0. So this already stems from this from these substitution steps, and now we want to go further, and in order to obtain more values, I2, I3, and so on, we have to analyze in more detail the second integral. I will go back. So we have to do from this first part, we get 3/4 and I1 is equal to 0. From the second part, we get the rest, and this, of course, will be much more involved. So what do we have to do with analytic combinatorics? We embed this into a more general function, and this function is now called J of Z and U. And I do a Taylor, or we do a Taylor series expansion around Z equals 0, because this corresponds to 1/n with n tending to infinity. And once we have such a Taylor series, we get an exact representation of our integral, and also an exact representation of IP of these coefficients, because this Z to the power P is basically 1/n to the power P. This is what we're interested in. And now analytic combinatorics comes into play, because we expand this here from we integrate not only from 0 to 2n, but from 0 to infinity. So we extend the integration interval from 0 to infinity, introducing each time an exponentially small error. But the problem is that these evaluations will become more and more complicated. They are doable in preferentially using a computer algebra system, but they get more involved. This means we know the dominant term, 3 over 4. We know the next term, which is 0. And then we are left with such nice or ugly evaluations which we have to do, and of course we'll integrate from 0 to infinity. So this is something we have to do, and when we do such evaluations from 0 to infinity, we require such integrals of such functions. And of course here is the point where these alternating multiple zeta values arise. And for example, we use this identity so that if we extend the domain of integration to infinity, not from 0 to 2n, but from 0 to infinity, then we have such an evaluation. And you see that here the alternating multiple zeta value, because here we have a bar over the argument p plus 2, comes into play. How to prove such identities? There are several different possibilities. Actually, we have offered two different proofs. Only one appeared in the final version of our article. One possibility is to consider the multiple polylog function with different parameters. This is basically a multiple zeta value with a power function combined, and then we can use well-known properties of this polylogarithm function because they satisfy so-called shuffle identities. And what does this, oh, there should be a B, I'm sorry. What do these shuffle, what does it mean? It means that you have two different strings of arguments and you shuffle them together similarly as you shuffle cards together. So this is the well-known shuffle identity for polylogs. And if you use this, then you can, because this ln of 1 plus e to the minus u is also a logarithm. This has this form. This is also a polylog, a very simple one. And we can combine this using the shuffle identity in order to evaluate this. So this is what we have in our example. We have such logarithm functions. We can relate them to the polylogs, to very simple ones. Then we use the shuffle identity in order to get such a representation. And this is basically already the alternating multiple zeta value. So this means when we do the Taylor expansion of the bivariate function, we are left with such integrals, and this means work for us. So we had to figure out such lemmata in order to see the connection to alternating multiple zeta values. So what can you expect from our work? We did this for many different integrals. And of course, you see that already I2 involves an ordinary zeta value, I3 involves an ordinary zeta value, and so on. And here different families of integrals arise, and we also had to evaluate them. This was very difficult. Basically, all I've shown you up to this point is what Guy already has done in his short note. And what is interesting here is that our basic evaluation is what I just told you, contains alternating multiple zeta values. Here you see them. But surprisingly, all these alternating multiple zeta values could be reduced to ordinary zeta values using known relations for alternating zeta values. But the thing is, this gets more and more complicated. So we needed more and more lemmata in order to evaluate the coefficients, and this got really ugly. So more terms could be were obtained in this fashion, but more and more complications. As you can see, it gets more and more involved in order to give you a short taste of what we did. So this we also did by hand. Sorry, I will put this down here. And then, for example, I6, you have such a very structured evaluation into alternating multiple zeta values, and surprisingly, all these alternating multiple zeta values could be simplified to ordinary zeta values. This was kind of a surprise. And what is notable here? The apparent regularity of the patterns for small p. So all these coefficients in the asymptotic expansions are of the same type. They are a sum of alternating multiple zeta values, and they could all be reduced to a rational polynomial in the ordinary zeta values. But in general, they cannot be reduced. So this is a surprise. For example, if you look at the alternating zeta values, zeta of part 3 and 1, if this alone appears, it seems that this has no rational expression of ordinary zeta values, but this is only a conjecture. This is not even known today. But it appears from the numerical studies that this cannot be related to ordinary zeta values as a rational multiple. However, in our evaluations, it seems that all the exotic terms stemming from the alternating multiple zeta value cancel out, and we are left only with very nice simple zeta values. And I will show you in the future that both statements are true using a much better evaluation. Yeah. And as I announced, this integral, this simple looking integral already gave rise to alternating multiple zeta values, and I will show you now how to do them properly. And actually this substitution was found by Moti-Levy, and this substitution will lead to a closed formula of this asymptotic expansion. Okay, let's go back to this integral. So we use the symmetry at 1/2 in order to get this first representation, and now comes the main point. We use a different substitution to get a much nicer form of the integral. So if you have a background in combinatorics, you already see that you have here more common powers of a logarithm function. So this substitution was a key to unlock this problem, because once we are here, we can expand this power into Stirling number of the first kind. So because there is a known identity, this is a generating function of Stirling numbers of the first kind. And of course, these Stirling numbers are also known to be related to so-called truncated multiple zeta values, which are basically generalized harmonic numbers. These are just nested sums which look like this. And if we use this improved substitution, then we get a much nicer representation of the whole integral. You do not have to do asymptotics, let n tend to infinity, exchange the boundaries of integration, introduce an additional error, but here we get an exact representation using the unsigned Stirling numbers of the first kind, or equivalently the truncated multiple zeta values. So you see here the exact representation. But we are left here with another integral, which is also left for us to do. And how should we continue here? You see, we already have here the asymptotic, the complete expansion, which is exact, but we need to evaluate this remaining term, which only involves, as a final task for us, this integral. Okay, assume that we know how these integrals evaluate. If we know how these integrals evaluate, then we can write them. If we assume that this is just a series expansion in powers of r with some coefficients beta sub j minus 1, then we have a closed formula expression, just rearrangement then, and grouping terms leads to an exact representation. So this means we are only left with such an evaluation. We need to determine the beta values, because then we can do the resummation, the rearrangement, the regrouping of terms, and we're left with a complete expansion. Here we have the 3/4, then we have the 0, and then here we have the IPs, which are basically these coefficients, these numbers here. So this means we have to dive into this problem now. We are now left with a simpler problem. How can we do here an asymptotic expansion or a complete expansion like that? And you see already that this problem involves much combinatorics. From one substitution leads to integrals, And another substitution leads to Stirling numbers of the first kind. And we will see on the next slide that also the Euler polynomials come into play when we want to determine these coefficients better to the beta sub j minus 1. Yeah, regrouping this. We can simplify this further and get here a complete representation of the searched values I sub p, which I mentioned in the introduction. We were basically interested in this, and this is where Guy Louchar's approach was from analytic combinatorics, and Michael Hoffman was interested in the strange occurrence of these alternating multiple zeta values and also their relation to the ordinary ones. So everybody had a quite different approach why he was hooked on by this problem. Okay, we still need to find these values beta j. How do we do that? Well, they are given in this lemma. They are just given by special evaluations of the Euler polynomials. Okay, this was a surprise for us that they can be really evaluated. You quickly how this can be done. Namely, how do we do it? We start with this integral which we want to evaluate. Then we do the substitution, which is announced here. U is equal to e to the minus t. And what do we recognize here? This looks very, very similar to the generating function of the Euler polynomials. So much more combinatorics comes into play, because the generating function of the Euler polynomial is of this structure. It's e of tx is 2 times e to tx divided by 1 plus e2 e to the power t, and this has an expansion, and these polynomials are then called Euler polynomials, and they have very, very interesting combinatorial properties. And what can we do? What appears in our integral is just, so this is the derivative with respect to the power t, so we just can do a few derivatives of this generating function and obtain what we have in our integrand. So this means the series we are interested in can be represented in terms of the generating function of Euler polynomials, and because we evaluate them at -1, here a -1 will appear. What do we do next? Of course, we expand this e to the minus rt in the ordinary way, interchange summation and integration, and then we obtain the stated result for the beta values, which I've shown you before. This is then the final result for the beta values, and this means also that we have an exact representation of our coefficients I sub p. So we were quite happy with this expression because we can do a further simplification relating the Euler polynomials at -1 to the Euler polynomials evaluated at 0, and this also is related to the Bernoulli numbers. So this, we have a nice compact closed formula for our coefficients of this integral, and it involves the alternating multiple zeta values. In fact, we have shown more. Namely, it was surprising for us that not only the alternating multiple zeta values appear, but also they could be simplified to the ordinary one. And this is where Moti and Michael Hoffman came into play, and they used result of Kölbig or Nielsen polylogarithm function, because they Kölbig related these two things, namely the alternating multiple zeta values and the ordinary one, and these results of Kölbig allow us to express the alternating multiple zeta value in terms of the ordinary one, and this is non-trivial that this can be done, and it cannot be done always, because for some special values of alternating multiple zeta values it cannot be done in general. So this is our final result. We changed here. I hope you recognize now this is now an ordinary multiple zeta value, but we have now here a sum of coefficients, and if we have an ordinary multiple zeta values with
Markus?
Sorry.
So it seems that it is even better than a polynomial in the zeta function. It's a linear combination of zeta function.
Yeah, I mean, we have a polynomial in ordinary zeta values, in not a single argument one.
Ah, okay.
Yeah,
Okay.
this is because we can reduce this furthermore to single argument zeta values using this this generating
Yeah,
function.
right. Okay, yeah.
Because here we have now a we have here now a multiple zeta value, and of course these special multiple zeta value where all the remaining entries here are ones can be related by a classical result to the ordinary Riemann zeta values, and this is what we have seen for I2, I3, I4, I5, and so on. And this is now the explanation why this happens. The explanation is that in this special case, the alternating values can be reduced to the ordinary ones, and the ordinary ones are of this special structure, and they can be reduced then again to the single zeta values. So, so this was kind of a surprise that we get a closed form expression of all this. So you can think now, oh, sorry, I will go back. So you can think, okay, this is a nice small problem in number theory and in analytic combinatorics. What is the point? Why should we be interested in such problems? And I will put now things into greater context by introducing random variables and convergence of norms. And this is the title of the second section. So I will introduce now a random variable and put this integral and where we did the asymptotic expansion in a much more general context. So previously in the first section, we derived a complete expansion using this clever substitution of moti. We were able to give a closed formula of this ISRP. But the question is, why this 3/4? And why should we be interested in these things? Of course, you can say from a theoretical point of view, this is nice. Analytic combinatorics meets number theory. We have some strange simplifications, some strange occurrence of multiple zeta values, both ordinary and alternating. But why are these values occurring? And now I will put the results into a wider context. So now probability theory comes into play. Let U denote a standard uniform random variable, and then I can define another random variable Z just by taking the nth power of this uniform, taking 1 minus the uniform also to the power n, and then I take another power 1/n. And of course, you may recognize this is the nth norm of a random vector. And why is this random variable interesting? Because if I take the expected value of this random variable, I'm just here at the integral we did the analysis in the first place. So you see, why was this interesting? Because we computed the complete asymptotic expansion of a random variable for n tending to infinity. Of course, when you do an expected value in probability theory, you are mainly interested in the raw moments or the power moments, as you want to call them. So we introduce now an additional parameter S, and we analyze not only the expected value, but all the power moments and look what is going on here. So this means if we take here the S raw moment, this means here our integral gets here an additional parameter. It's not 1/n, it's S/n. And also note that, sorry, I will remove this again. Note that the random variable I introduced before is just the nth norm of a random vector. And now, of course, measure theory comes into play, or basic analysis. And we all know that this is the 1 norm, this is the 2 norm. And of course, all these norms, the first norm, the second norm, the usual Euclidean norm, all these norms converge for n to infinity to the maximum norm, which looks like this. So we already know, this is what we learned in analysis in our standard courses, that we have convergence of norms, that the norms are not only equivalent, but that the second norm, the third norm, and so on, for n to infinity, they all converge to the maximum norm. This means that we know what this random variable should be. It should be the maximum of these two. And of course, we have convergence of norms. This is what was also discussed before the beginning of the talk, that this is what we get for free, that these families of random variables converge. I'm sorry. Yeah. And of course, the density of this one is given by, okay, this does, oh, now it disappeared. The density of this, of the maximum of is given by 2. So this means we have a uniform on this interval. And here we know the density. This is just constant 2. So this explains why it's 3/4. So from the theory of random variables and convergence of norms, I can explain why this value should be 3/4. And of course, once we know this limit law, so this is not really difficult to obtain, as we discussed earlier. This is just the maximum of a uniform and 1 minus the uniform. So here we can calculate all the moments for real S greater or equals 0. This is what we can do. But now we are interested not in the limit law, but we are interested in the finite random variable set to the n. And now we can have a look at the asymptotic expansion. How fast do the moments of this one approach the moments of this? And here's the theorem. This is what we got. Of course, the convergence of this random variable in with moments almost surely and so on. This is very well known. But our main contribution was that we get here an exact representation of the power moments of this approximation to this set infinity. So we looked at the nth norm of u and 1 minus u. Then and then we did again all the asymptotic analysis. So this is basically not the first line is the main contribution, but the second line is the surprising fact that here we also have alternating multiple zeta values here hidden, and also hidden the Stirling numbers inside, and we get an asymptotic expansion of the same type. So this was kind of a surprise for us that convergence of norms of such simple random variables already involve multiple zeta values and alternating multiple zeta values. And of course, before I showed you this for integer s, and if you do this for arbitrary positive real s, we also need the Bell polynomials in order to give a closed representation of the power moments of this one. Okay. How did we do this? We proceed as before. We use Motis substitution. And we have a new difficulty here because we have to do such an evaluation of such a family of integrals. And this is now much more involved than we did before, because the big problem here is that we have now not a 3 here in the denominator, but we have a variable s. And we want to expand this again, and we want to see again the Euler polynomials and so on. But here we proceed a slightly different way, because we use the logistic function, which is just a special evaluation of the generating function of the Euler polynomials. And here we can see that we have here powers of the logistic functions and their derivatives. And the main problem is now, how do we get an expansion of these blue terms into the coefficients of the Euler polynomial generating function? And this can be done using a very important first step. Namely, here another topic comes into play, namely the derivative for polynomials for the logistic function. Namely, we have the following result. For all positive integers r, the derivative, the r minus 1's derivative of the logistic function can be written as a polynomial in the logistic function itself. This means if we differentiate r minus 1 times with respect to the variable t, then I have a polynomial in my function itself with some coefficients. And interestingly, these coefficients involve the Stirling numbers, not of the first kind, but of the second kind. And we need this because we want to relate later on these things to the generating function, to the Euler polynomials. Okay, how can this be done? I will offer you two different proof strategies. One is Hoffman theory of derivative polynomials. This is what we used in the paper, in the article. I will present you a slightly different one. Namely, it can also be done in another way. Namely, just obtain a recurrence relation for this value and then partial differential equations. And this is what I will show you, a short proof of this, because we use we differentiate the logistic function, and from a comparison of coefficients, we obtain a recurrent relation with some initial values. And we now use standard tools from combinatorics, namely we introduce a bivariate generating function, and normally we can relate recurrence relations using generating functions to functional equations or to differential equations. And here with this kind of recurrence relations relation, we are left with a partial differential equation of this type. And of course, some such partial differential equations can be solved first order, linear, can be solved using the method of characteristics. And once we have the solution, we can extract coefficients to get the search numbers, which are C, R, J. And this is what we did. We used the method of characteristics and we derived the first integral of the system, did a change of variables, and then we obtained at the end, we did a transformation to these new coordinates, and using standard methods from partial differential equations, we found our generating function, which looked like this. So this is all standard theory from partial differential equations. The main problem here is that you need to adapt to the initial condition, and once you did that, then you have the bivariate generating function. And of course, if you are fluent in combinatorics, you recognize this. This is closely related to the generating function of the Stirling numbers of the second kind. And once we extracted here the coefficients, they generate the Stirling numbers of the second kind just popped up. And this is how we get our lemmata. Don't forget, we needed this lemma in order to evaluate the integrals, in order to get the moments for a more general random variable. And in the second step, we solve this expansion, but for powers of the logistic function to obtain another kind of coefficients. And in combinatorics, it's known that the Stirling numbers of the first and second kind, they are inverse in some sense. And this is how the Stirling numbers of the first kind, how we ended up with them. So this led us to a proof of this complete expansion of these power modes. And what were additional byproducts of our study? I showed you the slide before where I showed you the complete expansion of these moments. We have a rate of convergence. We can give, using the Barrier-Sein theorem, I can give a rate of convergence. Of course, the convergence in distribution can be strengthened to almost sure convergence. And there are also generalizations to beta random variables when we take the nth norm, not of a uniform, but of a beta and 1 minus beta. So we see that the same phenomenon occurs not only with one integral, but with a whole family. And this family of integrals stems from some random variables, which are nth norm of random vectors, which was quite a surprise for us. And is this a unique effect? Does this only occur when you look at these norms? And the answer is no. You can also consider variations and put this into a much more general context by considering families of IID random variables. And there you will see that this is actually a general phenomenon that alternating multiple zeta values will occur. So here now I will consider, in the final part of my talk, I will consider now IID uniform random variables, so they're independent and identically distributed, and I will look at the random vector of all IID uniforms. And what can I do with a random vector? Of course, I can take the nth norm. This was the idea before, in order to relate the integral from the beginning to a much more general problem. And of course, we know what happens when n tends to infinity. Then, of course, the nth norm tends to the maximum norm, and the maximum of these uniforms, this is now an order statistic, is just a beta limit law. So we know the limit here, but we are interested in the finite n asymptotics of this random variable Wn. And as it is written here, we are now interested as in the asymptotics of this. We know the limit law, so this is very simple, but we are interested in the asymptotics of the moments. And now the integration gets much more messy, because we now integrate over an R dimensional cube here. So you see the integration becomes more and more involved, but I will show you that this structure that alternating multiple zeta values occur, this stays basically the same. And of course, you can take here different kind of random variables. You can take here exponential IIDs and so on, and you will always have the same phenomenon. So what was our result? Oh, sorry. For I equal 2, you can compare what we do now with the basic problem I considered at the beginning. In the beginning, I was interested, or Guy was interested, in a complete asymptotic expansion of this integral. Now we know why this is interesting. This is just the nth norm of this random vector. And here in the IID case, I'm interested in the nth norm of a random vector of independent uniforms. So here these random variables are not independent. I have u and 1 minus u. This is the same random variable. And here I have 2 independent uniforms. And here the integration is a little bit more difficult. But the integration is more difficult, but we still have an exact representation using basically the same tricks and methods as we have before. For R equals 2, we have a closed formula, but for general R, we only have asymptotics. So this, of course, is the est moment of the beta limit law. And here we get some correction terms, and all the correction terms are related to multiple zeta values. This was kind of a surprise for us, that this phenomenon stays the same. And if you want to put this into a more general context, then you can replace the IID uniforms by different families of random variables, and using the same approach, you will see that alternating multiple zeta values should appear in the finite n expansion of this. Okay, for R equals 3, already some strange things go on. So before you see that here, I only gave you an expansion up to the order 2. And the reason is that even if I have 3 independent uniforms, then more and more involved things arise here in the exact representation, because you see I have here now alternating multiple zeta values, but also the complete expansion also involves alternating sums, where we have much more complicated objects. I have here as theta star values, which are also nested sums, which are very closely related to the ordinary multiple zeta values, but these things get more and more complicated. And it was kind of a surprise, a big surprise for us, that in the IID case, more and more variations of multiple zeta values appear in the limit. So this is very intriguing, and we don't know why this is like that. Namely, in the R equals 3 case, we have these kinds of nested sums, and they are also zeta values, but they are different zeta values. Namely, they are Arakawa-Kaneko type zeta values. So Arakawa and Kaneko, they are 2 Japanese mathematicians, and in their study of multiple zeta values and the relations between them, they introduced the so-called Arakawa-Kaneko zeta function, which is defined like this, using a polylogarithm function. And I've showed I think 10 years ago, that the Arakawa-Kaneko zeta function has a representation like that. And you see, this is exactly what we have in our integrals, in our expansions here, just that these things are alternating. This means this double sum, or this sum here, is a variant of the Arakawa-Kaneko zeta function. Is just an alternating one. So this is really surprising for us. This was really surprising for us, that more and more different families of zeta values appeared in these asymptotic expansions. And the reason behind this is unclear to us. It's just like that. So it seems some tip of the iceberg of a general phenomenon. And yeah, as I mentioned before, this alternating series is just a modified, you can call it a alternating Arakawa-Kaneko zeta function, and so on. And if you look at more cases, so R equals 4 and 5 and so on, more and more intriguing all variations of multiple zeta values appear. So this is really surprising. And at the end, in the last 3 slides, I will give you some more strange results, namely for concrete values of n. Of course, you can do the evaluation of these integrals. It's no problem. So this is what we started in the beginning with an expansion of this. And if I plug here in n equals to 2, I get an exact representation using the logarithm function. On the other hand, if we consider our results, if we just consider our results, then we have here a very intriguing representation, or a very intriguing identity relating alternating multiple zeta values. Here we have the counterpart with the ordinary ones with the logarithm function. So a byproduct of our study is that such really strange identities involving the Bernoulli numbers or the Euler numbers. And if another one is when you consider the IID case, and then we have also very intriguing identities, and this is really surprising in some sense. At the end of my talk, I will give you some open problem and current work I'm involved in. Of course, what is missing here is the structural explanation. Why does I of n involve ordinary zeta values, whereas if we look at the IID case, we have the alternating multiple zeta values? Then, of course, a structural explanation. Why does these finite n expansions involve zeta values at all? This is really strange. Why do they appear here? They appear in many different places in mathematics, the multiple zeta values, in the Gumbel distribution, the quicksort limit law, and in physics all over the place, but also here. But we don't have really a nice explanation why this appears. Then another current work is a more detailed analysis of these alternating multiple zeta values and their relation to Euler numbers. This is more related to number theory, but it also has applications to the raw moments of the random variables which are introduced before, which are the norms. And we are also looking at the moment at additional occurrences of multiple zeta values in related problems, putting these kind of phenomena into a more in a much broader context. So this is what we're looking at the moment. And I have to thank you for this attention and this journey into number theory, combinatorics and probability theory. Merci de votre attention und vielen Dank für die Aufmerksamkeit. Thank you.
Thank you, Markus, for this nice talk and for these nice identities. Are there any questions, please?
Okay, I have some questions.
Yes.
Do you know if there is a natural generalization, multivariate generalization of the Gumbel distribution, such that the moments or perhaps the cumulants are leading to multi-zeta values?
I don't know if there's a multivariate generalization of the Gumbel distribution. I'm not sure about this. I don't know. I'm sorry.
And also there was this conjecture by Donzagier that the algebra generated by the if you grade them by their weights, you have a dimension, and the sequence of dimension was following the type of Fibonacci recurrence.
Exactly.
So it is expected that you will always be able to rewrite them in terms of other ones. But here you get something which is which reduces much more than what is possibly expected. So do you think that there is a kind of sub-algebra of this MZV for which you have those relationships, and that all those problems are in fact in this sub-algebra of MZV? Or can you really get any MZV?
I don't know if this is really basically what we did is because we have very, very special alternating multiple zeta values. So what we always obtain is not the ordinary multiple zeta values, but the alternating. And these families are much bigger than the ordinary ones, because it is conjectured that some alternating multiple zeta values are independent over the rationals to the ordinary one. This is what I mentioned in the talk, that zeta of bar 3, 1 is independent of all the ordinary multiple zeta values. And in our work, basically, we exploited and the result of Kölbig, which related this alternating to very special multiple zeta values. And so we did not use this general theory of multiple zeta values. We only had one kind of alternating multiple zeta values stemming from the natural logarithm, and we could relate them then to the multiple zeta values. So basically what we encounter always is the alternating families, not the ordinary ones. And the alternating families are much, much bigger. It seems like that, but this is only a conjecture. So they are even bigger than the ordinary ones.
And what is striking also is that, okay, you are doing some type of analytic computations.
Yeah.
At the end, you get really a lot of quantities which have a combinatorial name, which are
yeah.
So it is kind of suggesting that perhaps there could be a more combinatorial proof of those phenomenon. And perhaps one of the key for this is the shuffle that you mentioned. So it's quite often it's possible to enter this integral, this MZV as words. Their identities between them become some type of shuffle of words. Did you try to interpret, to go to the word representation of this and try to see if by playing with words you could get those identities?
Actually, in the beginning, we did it like you just mentioned. We looked at these identities which stem from the shuffle or stuffle algebra,
exactly,
where you do it with words. But then but here the problem was it was also we were stuck with finite values. We did not have the right approach, and the Euler polynomials, they enabled us to do everything at once and to be exact, because with analytic combinatorics we were stuck at one point, because we do with computer algebra all terms but only finitely many, because with the computer you get stuck at one point, but with the Euler polynomial approach, with the better substitution, you get everything for free. But and this also carries over to the IID case. So this is a general phenomenon. If you do uniforms, if you do betas, if you do exponentials, you could a meta theorem, if you want to, that you always have some alternating sums when you do the finite n expansion. But we did not put this in the article.
And in computer science, there are also stuff like, for example, quad trees for which some type of MZV are appearing. Try to consider if in those problems, if you push further the asymptotics or the asymptotic of the moments, if you have in fact even more MZV at higher orders, the one which you are already observed.
I think so. So for example, not only in quad trees, as also in quicksort, as I mentioned, if you look at the cumulants, and if you look more with more details in the structure of these moments, then you see, okay, zeta values appear, but why? This is another story.
Okay, thank you.
Welcome.
Other questions, please? Are there other questions? Yes, Dr.
I would like just to clarify some points. Then, if I understood well, you were mainly focused on the relation with the multiple zeta expressions, rather on the convergence, because your expressions are all your expressions are bit with uniform or Dirichlet distributions with functionals. let's say Dirichlet distributions, and these functionals always converge to the maximum, right?
Yeah, exactly. Yeah, yeah.
Okay. Then you have convergence in the almost. Actually, you have convergence in the almost sure.
Sure.
Way.
Yeah, of course. Yeah. Oh, yeah.
Okay. Then I found it very, very nice. This all the connections you made with very well known mystic special functions.
Yeah, it's really thank you very much for this nice comment remark. It's really intriguing that even if you take IID's uniforms, then you are led to strange multiple zeta values. This Arakawa-Kaneko zeta function, this is very specialized in number theory. And it was a surprise that it appears in probability theory when you look at such simple things. So we know the almost sure convergence of these functionals, of these norms, but such strange zeta values pop up and we don't know why. Yeah. Mm-hmm.
Thank you.
Welcome.
Other questions, please. Are there other questions? So again, thank you for this nice talk, Markus. Thank you for all the public. And this is the end of the seminar today. Thank you, Markus.
Thank you.